Here are a few examples on how to find exact area under a curve in calculus using summation notation. Let's look at this. There's a general formula that we use. That's our basic setup from Riemann Sums, where f of x is the height of your rectangle, delta x is your base, and we're going to do an infinite number of rectangles. So a couple of formulas that will come in handy. And the first example is this one. So I'm going to start with just the general formula. It's the limit, and that says limit if you can't read, as n approaches infinity of the sum of f of x sub I delta x as I goes from 1 to infinity. Until you get really good at this, I would recommend you just write the formulas every time. Makes it easier to remember it. X sub I is your initial value, which in this case is 0, plus delta x times I. And I need to actually find out what delta x is. Delta x is b minus a, so 1 minus 0 divided by n, which is just 1 over n. So over here, I'll plug 1 over n in for delta x. And for x sub I, I'm going to clean that up a little bit. That's going to be 0 plus 1 over n times I. Oops, that was right. There, 1 over n times I, which is just I over n. So I'm going to plug both of those in here. So this will become the sum. I goes from 1 to infinity of f of I over n times delta x, which is 1 over n. And f of I over n, if we plug into f of x right here, f of I over n, 1 to infinity of I over n squared times 1 over n. And I will clean that up. I goes from 1 to infinity. That'll be I squared over n squared times n would clean up to I squared over n cubed. And then the n cubed is a constant as far as the summation notation is concerned. So I'm going to take that 1 over n cubed because that's a constant. And I prefer to take that out of the summation notation and stick it in front just to get it out of the way, make things a little less ugly. So now I've got the limit as n approaches infinity of 1 over n cubed times the sum as I goes from 1 to infinity of I squared. Now there are some formulas for the sums of the first integers, the first n squares, the first n cubes, and all that mess. This summation right here, the sum as I goes from 1 to infinity of I squared, the formula for that, and you really just kind of need to know these, is n plus 1 to n plus 1 all over 6. And then that is going to be multiplied by the 1 over n cubed in front here. So it's 1 over n cubed times that, and we are still doing the limit as n approaches infinity. And then if you look at this, if I were to expand it, my numerator and denominator have equal degrees. If I were to expand the top, I would expand, and I would have n times 2n, which is going to give me, stupid announcements. Well, that was just rude. Okay, so I have n times 2n would give me a 2n cubed. And if I were to do a full expansion, there will be a bunch of other gunk that doesn't matter. My denominator is just 6 times n cubed. And there's nothing else down there. Top degree does equal bottom degree. We can divide coefficients, and the answer is 2 over 6. And if you're really smart, you could reduce that to 1/3 for your exact area under the parabola x squared from 0 to 1. So there is an example of how we can use summation notation, Riemann sums, and tweak it with an infinite number of rectangles to generate the exact area, no longer an approximation. So getting to an uglier example, and this one's going to be bad because my interval does not begin at 0. An interval that begins at 0 is really nice because if it begins at 0, then your x sub I is 0 plus something, and it cleans up your x sub I. If your interval begins at a non-zero x coordinate, then it gets a little bit worse. So my delta x, I'm going to start by finding that. That's going to be 3 minus 1 over n, or 2 over n. X sub I, or not delta x, x sub I is your initial value, a, so 1, plus your delta x. Son of a... Okay, I think the announcement's over now. Hopefully they won't do any more. So my x sub I turns into 1 plus 2I over n, and those are what we're going to plug into the general formula, which is this. There it is, magically appearing. So plug in those things in. So f of x sub I, so that's f of all of this stuff, 1 plus 2I over n times 2 over n. Right? And then we're doing the sum of that as I goes from 1 to n. And f of 1 plus 2I over n is going to be 1 plus 2I over n squared plus 1. All of that. I'm just plugging the 1 plus 2I over n in for x here, and I still need to multiply that by 2 over n. And then we need to do a full expansion of 1 plus 2I over n squared, and we need to clean all of this up, which I'm going to save you the boredom. I'm going to pause this and finish that up, and in about 2 seconds you will see what it simplifies to. There we go. So I squared out 1 plus 2I over n. I combined 1 plus 1 to get 2. This right here, this piece, wait a minute. This piece right here is this piece simplified. Then I'm going to distribute my 2 over n, and when I distributed 2 over n, I ended up with all of this stuff right here. And now I'm going to split up my summation, and at the same time, I'm going to recognize what my constants are, which is anything that does not have an I, and I'm going to write those in front of my sigmas. So the sum of 4 over n, I could pull that 4 over n out and make that the sum as I goes from 1 to n of just 1 plus, and then I can pull the 8 over n squared out and do the sum as I goes from 1 to n of just I plus, and then for this I squared one, I can pull the 8 over n cubed out. 8 over n cubed, sum I goes from 1 to n of I squared. Okay? And then now I have some simple summations here that have very nice formulas. The sum of the first n constants of 1, the sum of the first n integers, and the sum of the first n squares, which those formulas are, that would be the sum from 1 to n of just a constant is going to be n. The sum of the first n integers is n plus 1 over 2. And then the sum of the first n squares, this is the ugly one, is n plus 1 to n plus 1 over 6. And then don't forget that the 4 over n comes along with it, plus 8 over n squared times that, plus 8 over n cubed times this one. And once again, like the last problem, we have a bunch of situations where the numerator and denominators have the same degree. And so a little bit of fuzzy math here. First, this one's not fuzzy. Those ends will divide out, leaving you with only a 4. This one right here, 8 times n would give me an 8n squared and other stuff, which doesn't matter because n squared is my high power term, over 2n squared. And then I have 8 times n times n times 2n, and I'm focusing on my high power terms. That will be 8n cubed times 2 is 16n cubed, plus a bunch of other stuff that's insignificant because I only care about the high power term, over 6n cubed. And now finally, when you divide their leading coefficients, you get an answer of 4 plus 8 over 2 is 4, plus 16 over 6 is 8 thirds. So 8 plus 8 thirds is 32 thirds. And so there's your answer. Let's try one more. This one's going to be a little bit nicer because I am starting at 0. So again, I'm going to start by finding my delta x and my x sub I. Delta x is b minus a over n, or 3 over n. And x sub I is going to be my initial value plus my delta x times I, which cleans up to just 3i over n, and that's going to make this one nice. Number 2, the second one ended up being really bad because my x sub I ended up being a binomial, which forced me to do an ugly expansion. This one, my x sub I is a monomial, so it's not going to be too bad. So my general formula is right there. And we're going to start substituting in everything. So that was a horrible vertical line. There we go, that's a little bit better. I equals 1 to n. F of x sub I is 3i over n times my delta x, which is 3 over n. And then I'm going to find f of x sub I by plugging x sub 3i over n for the x's here. So that's going to be 2 times 3i over n cubed minus 3i over n squared. And then all of that is my f of 3i over n, but I still need to multiply it by the delta x, the 3 over n on the side. And let's expand and clean this up. There we go. There's the expansion, the full expansion of all this stuff. And now that I've gotten to this point, I can break up my summation notation into the difference of two sums, and I will pull out any constants, that being the 162 over n and the 27 over n. So I have 162 over n times the sum of the first n I cubes, or cubed integers, whoops. I goes from 1 to n. And then here I'll pull the 27 over n out. I goes from 1 to n of I squared. And now again, we need to use our formulas. The formula for the sum of the first n cubes is n squared, n plus 1 squared over 4. And the sum of the first n squares is n plus 1, 2n plus 1 all over 6. And we will keep these constants in front. So we have 162 over n times that minus 27 over n times this one. And when I look at that, I notice that I have 162. Oh, hold on, something's not right here. Okay, a little error I made, and I'm going to let y'all learn from my mistake. In the end, for these types of problems, if you're finding the area under a polynomial, you should notice in the end that your degree on top and bottom is supposed to be the same. So my degree here on top and bottom, I have n squared and n squared. I should have an n to the fourth. I should have an n to the fourth down here also. Similarly, over here, I have n, and 2n. That's an n cubed. I should also have an n cubed for this one on bottom. And my mistake was way over here. I was trying to expand too quickly. I did 3i over n cubed. I cubed the 3i, but I forgot to cube the n. So that should be an n cubed down here. Similarly, 9i squared, or 3i squared is 9i squared, and I forgot to square the n. So that should be an n cubed. This should be an n squared. And then when I distributed this 3 over n, that should have given me an n to the fourth and an n cubed, n to the fourth and an n cubed. N to the fourth, n cubed. So there, now it's looking right. So that's one thing you can do kind of as a little safe check. You should, if you're doing this with polynomials, end up with degrees on top and bottom being the same, and now I do. If I were to expand that, that's 162, n squared is going to give me 162 n to the fourth, and a bunch of other stuff that's insignificant because that's the high power term, over 4n to the fourth, minus 27 times n times n times 2n. I'm only multiplying out the high power terms. Would be 54 n cubed, and there will be some other stuff that I don't care about, all over 6n cubed. And so finally, when you divide those leading coefficients, we get 162 over 4 minus 54 over 6, which reduces to 63 over 2. And there, finally, we are done. So there is using summation notation and infinite limits to generate exact areas under polynomials. Polynomials do tend to be very nice, and I don't know, you may not believe these are nice. But there we go. That's long enough. Bye-bye.